All right. So a reminder from before, overfitting is when the validation set loss starts degrading even while the training set loss continues to improve, right? And there are a couple of ways that we can think about this. One that I find sort of, particularly useful, I guess, is to think of it as the network learning, or to think of it as the network memorizing the input rather than learning a general rule, right? So graphically, right? Again, reminder, overfitting is when the training set loss sort of keeps doing this, right? Where the training set is the data you are training the model on directly, but then the validation set loss, in the extreme case, does something kind of like this, right? And I really have seen it this bad or worse, right? So if we just look at our training loss, right, we think we're doing great, but then when we look at our testing or validation loss, we discover that our network performs horribly on unseen data, right? Regularizers are things that fight this trend, that help us keep the validation loss more in line with the training loss, right? And ideally they do it without destroying the network's ability to train, right? I was about to say they do it without causing the training loss to be terrible, but we don't really care, right? Validation loss really is the metric we care most about, since we care most about what our network does on unseen data, right? Okay. Where did you go, LibreOffice? Resume slideshow. So there are a bunch of, so we talked before in the capacity and data chapter about overfitting and about some of the sort of basic steps we can take to fight it, right? Again, it's been known for a very long time that the more capacity our model has, the more subject to overfitting it will be, and so one sort of fairly easy way to combat overfitting is to just reduce the capacity of our model, right? Pick the lowest capacity model that can still be trained on our problem. Another one is to use more data, right? More and more diverse data pretty much always helps our network train better. A third, and sort of somewhat trivial one, is just to stop training early, and I wish I hadn't erased that graph now, right? So by stop training early, come on now, what I mean is, if we know our graph looks like this, we do a couple of runs to estimate where about this point is, and then we just stop training right there. Right? And you can keep a running average of validation losses and simply abort when the validation losses start to get worse. Or you can do this empirically, right? Run a bunch of tests, get a good guess for where this point usually is, and just stop there, right? But we also have some more sophisticated tools at our disposal, right? So a classic one is a thing called weight decay, right? Weight decay adds a penalty to the loss for having large weights. That looks like this, right? L is whatever loss we like. That might be mean squared error, for example, right? And remember that L, the loss, is a function that, didn't leave myself enough room to write, right? L, the loss, is a function such that high L implies bad performance and low L implies good network performance, right? We create a new L, which I'm just marking as L decay, by adding a term that is just the almost kind of the L2 norm of the weights. And again, basically don't. So what I mean by L2 norm is basically how mathematicians talk about distance, right? That's your good old Euclidean like x plus y squared root like distance formula, right? So it's basically the distance formula, but of all of the weights, right? And this is another term, right? That when the weights are all small, when the sum of the squares of the weights are small, right, will be very small, and then when the squares of the weights are large, will be very large, right? So our new loss is our old losses signal plus a signal that encourages the network to use weights very near zero. And I say almost because I think it would correctly be that. It would be the square root of this to be the actual L2 norm. Oh, wait. It would be the square root of that to be the L2 norm. But close enough. So when you do the math, you essentially get this, right? The new calculus-derived rule, calculus chain rule-derived rule, is learning rate times our old weight update, right? We could just put a paren right here, right? Our old update plus this, 1 minus lambda times w. So it's our old weight update times a thing that just slightly shrinks the weights, right? Just slightly pushes them towards zero and doesn't depend on the input or any other complex term. And that's loosely analogous to writing this, right? Step 1, use the old weight update. Step 2, very, very slightly reduce the weights, right? This, right, something very near 1, 0.9999 times w, is equivalent to like 1 minus lambda w, when lambda is very small, which it almost always should be. So it basically ends up, so we end up with something very similar to this, right? And so again, I say very similar for reasons we'll talk about in a minute. This is a reasonable approximation to the result of this loss. Oh, yeah. I couldn't run down the earliest citation for this. I saw this thing cited for weight decay, but I couldn't get into it to read it. It's behind a paywall. This is the earliest non-paywall citation I could find. And don't know why I bother mentioning that, because I don't really expect y'all to, visit these, but whatever. All right, so technically, if I say that weight decay is just adding this after the weight updates, that's kind of close. No, come on, man. Draw a straight line. All right, close enough. This is only correct if we're using stochastic gradient descent without momentum. Right? There are other optimizers for which this would not be the correct result of adding the L2 of the weights, right? But it frequently works well, even though it is technically wrong. A lot of people sort of used this form even though it didn't line up exactly with the math. And hey, it ended up working, right? Debatably, I've seen at least one person use the two terms differently. I've seen at least one person refer to weight decay as this, no matter what, and then L2 regularization as the result of adding that thing, right, this, to the loss, and then treated those things as sometimes being different, right? But other people don't maintain that distinction. It's kind of a thing where the language gets blurred, right? In fact, weight decay has been chewed on for more than 30 years. There are a bunch of slightly different formulations for it, explanations for it, intuitions about it, and implementations of it, right? So this is one of those times where a bunch of people might use the same word to mean very slightly different things and not bother to be clear about that, right? So we have that parameter. Yeah. So we have that parameter, right? We have the parameter that I explicitly noted as lambda, and then I just kind of picked a small number here, right? Well, okay, the result of 1 minus a small number here. You can pick other values besides 0.9999, but you should make them like this, right? You should you should use 1 minus something tiny. If you think about it, multiplying our weights times 0.9999 is not going to cause them to reduce by much, and it shouldn't. Okay? You want the weight decay term, right? You want the change to the weights caused by this, in general, to be smaller than the change caused by the normal sort of gradient-driven, error signal-driven weight update, right? So you want dW, like MSE, to be larger than, or comparable to, dW, like decay. If it isn't, weight decay will drag your weights to 0, and you won't be able to do anything about it, right? Even as your network gets worse and wronger, if the weight decay term is as large or larger than the mean squared error term, your weights will be hauled to 0. So you want this number to be, or you want the effect of this to be little bitty, so you want this number to be very close to 1, right? So Tensorflow uses the sort of L2 penalty formalization of weight decay. You can enable it by adding these to a dense layer. So these are optional parameters to the dense layer. We have been using the default of none. You can set keras.regularizers.L2, right? And I think that's going to be squared. I think L of 0.01 is okay, because I think it's going to get squared, which will turn it into an L of 0.0001, right? Which will be small enough to not swamp it, I think. But you can experiment with different values and see what kinds of behavior you get. So, Dropout is a more recent regularizer. Here is the citation for Dropout. Dropout was someone's master's thesis. I am more jealous than you can ever possibly know. The idea behind Dropout is pretty simple. During the forward pass, and I should say while training, randomly set a unit, or each unit, to 0 with probability p. So each unit has a p probability of being set to 0 instead of whatever it was going to be. So there are a couple of different ways to interpret what Dropout is doing, even though it's perfectly mathematically straightforward, right? There are multiple intuitions for why it works. One interpretation is that we're randomly sampling many similar networks that share weights. So what that means, the way that the original writer thought about it, was if you have... That neon green is a little bit hard to process. Let's see what this is going to be. Okay, that works. If you have an input like this, and then an output, we'll also use 3. Right? If you randomly turn each of these off, right? If you randomly turn this unit off, then that is the same in the author's mind of sampling a 3-to-2 network that happens to share weights partially with your original 3-to-3 network. And likewise, if you shut this one down but leave this one on, that is the same as sampling a different 3-to-2 network in an ensemble that shares a bunch of the same weights with the other two networks, right? That's how the original author thought of it, is as an extreme form of sampling an ensemble of networks that share weights. Another interpretation is that Dropout is just an extreme form of noise, okay? It's been known for a long while that noise can help regularize a network, and Dropout can be viewed as an extreme and very particular form of noise. Dropout is pretty simple in TensorFlow. Dropout is also just a layer. right? So kind of like batch norm, it just goes between the waits and activation of one layer and the waits and activation of the next one, right? And here I have used p equals 0.1. So each network at each output at every given step has a 10% chance, a 1 out of 10 chance, right, of being set to 0. Oops. So, note that dropout is only applied during training, not during testing, right? There would be no statistical, there wouldn't really be any gain during testing time. So this is a problem. It means that the average of each layer's output would be different between testing and training, right? So if you have a P of 0.1, right, then you are normally reducing the magnitude of the total output of a layer by 1.0 times P, right? Or for example, 0.9 in our case, right? Because 0.1 out of 1, right, 10 out of 100 of those nodes will be turned off, right? Will go to 0 and they won't contribute to the sum of the input, right? So to keep that in kind of the same range, you have to do something. In the original paper, they multiply the layer's output by P during testing, all right? I think I might have that wrong, so I think it should be 1 minus P. I'm not sure. I think it should be 1 minus P. But basically, during testing, they scale the output down, right, to represent the fact that more units are on average than would have been on during training. In the Tensorflow version, instead, they scale up the not turned off units, the ones that survive, if you will, during training, and then do nothing during testing, right? And again, both of these are ways to kind of try to keep the output range, the magnitude of the output the same between testing and training, even though during training you're turning some of the units off at random, right? So again, we see that there are two slightly different formalizations for what this thing does, right, that you kind of have to pay attention to notice the difference. I think one motivation for the change is that so that the TensorFlow version can just completely deactivate during testing. Because both the deactivation and the scale up occur in training, the TensorFlow network in testing can just be a no-op, right? The TensorFlow dropout layer in testing can just do nothing. Whereas this version of it, you have to keep the dropout layer and you have to have it do something during testing. Yeah. So noise, dropout. If dropout is an extreme case of noise, you also can just add a small amount of noise to regularize your network, right? And again, this makes a certain kind of sense. If we think of overfitting as the problem of our network learning specific features of the input, one way that we can kind of prevent that is by breaking up our input a little bit, right? By adding small random values so that the same input appears slightly different every time. Okay? I could not find a good overview of using noise for regularization. I can say there are a bunch of different schemes for doing this. You can add noise to the output of a layer or to the update. I have seen noise used for the like noise added to those DWs during updates. You can add it to the input, to some of the layers, or to all of the layers, and you can use different distributions and magnitudes of noise. Right? There are a lot of different ways to do this. And by noise, I mean, of course, a small random value, right? And at least with the functional API, you can add a small random value to a layer like this, right? Here I have my layer X, and I am just adding normal meaning zero-centered, right? Well, okay, meaning a little more than zero-centered, meaning also normally distributed, but so zero average, normally close to average, right? With a very small standard deviation. I made that more complicated by trying to explain it. All right. So I'm adding normal noise, right? I'm adding noise that will be near zero, right? That will be centered around zero and that will be clustered very tightly. So a very small amount of noise to my input, right? And that's just it, right? I get a random tensor, I add it, that's it. There are many other sort of things you could tune about this. Oops. And I meant to have a final slide to review. I meant to have a final slide to talk about sort of when to use these things, right? Because we've talked about a couple of regularizers. One critical thing I didn't tell you is when to use them, right? So I'm going to say real quick. All right. Don't use too much. Almost any regularization is going to have a trade-off, right? It will slow training a little bit, and it might degrade performance a little bit, right? Which, again, we strictly speaking don't really care in the final analysis about training loss. We only care about validation loss, right? But we care about sort of slowing learning. And too much regularization will prevent the network from learning at all, okay? So we don't want to use too much of it, right? We might, in fact, start with a totally non-regularized network. And I'm going to get something that isn't purple on blue. Let's see what 4 is. All right, that's a little bit more readable, right? And see how bad our overfitting is. Then add small amounts of noise. I'm sorry, add sort of small amounts of regularization, not just noise. And see how much of an effect it makes. Okay? And then add it incrementally. Increase incrementally. Right? And see if you can sort of see at what point your validation loss stops improving and make sure it helps at all. Right? It is possible. So it is possible for your problem to be ill-posed. It is absolutely possible that you might just not have enough data to do what you need to do, right? So, okay. Point 3, right, is regularizers aren't magical. Right? I have seen people just try to throw more and more regularization at a problem or at a model when the problem is they just don't have enough data, period. Okay? It is possible to have a data set that is much, much smaller than your model's capacity, right? And then you're out of luck. No amount of regularization will save you, right? So to kind of rewind to the step 2, pay attention to what happens, right? Increase your regularization slowly. Make sure it's actually helping. Be aware that your problem might still be impossible. Okay? What are good regularizers to pick? Dropout's pretty popular. I would start with a fairly small value for P, 0.1 or less, and see what you get. Weight decay. I guess weight decay is a good second choice. The issue with weight decay is that for L that isn't really, really tiny, right? So as L gets larger, you will very, very quickly obliterate the network's ability to learn, right? So with weight decay, there is a very, very careful balance around L. Around L or lambda, like the controlling parameter, right? where there is, in my experience, a narrow, unstable sort of little envelope between L too small to do anything and L too large for the network to learn at all. And tuning L can be a little bit tricky. Okay? So I think I would try Dropout first, and I would try Weight Decay second, and I probably wouldn't combine them unless I was desperate, I suppose. Okay. Right, and we don't have a code sample, or I wasn't planning on doing a code sample this week. Because again, these are all just layers, right? Noise is like a single line in the functional API. Dropout's a layer. Batch norm is a layer. Weight decay / L2 reg is a parameter on a layer, right? So none of these are particularly complicated if you already have a defined model. Okay? All right, sorry everyone. I feel like that lecture was not my best work, but that is regularization. As we've seen, at least one bit of it, the batch norm, very much kind of lives in the world of the vanishing gradient problem, right? I think that is that. So, what is on the list for next week?